Welcome everybody to this month's New Zealand Hydropower Group seminar. We've got Chesterton here with us, and they're going to be presenting on enhancing hydropower efficiencies with engineered polymer seals. So a big thank you to Michael Wahinger and Adam Powell, who are here on this call. As you know, Chesterton are a specialist company in sealing systems, and they're going to be presenting on this particular topic today. Not a topic I claim to be an expert in, being a civil engineer, as a number of you know. So I'll not waste any more time and hand over to the experts who will take you through today's presentation. So thank you, everybody, for coming.
Thank you, Andrew. This is Michael Wahinger here. And once again, I really appreciate the opportunity for us to present to you another very technical application I guess issue or experience that Adam in particular has many years experience with. And this follows on from last year where we had our main shaft sealing presentation. So I really appreciate everyone coming back to listen to this one. But Adam's the expert. I'm going to pass it over to Adam. So thanks, Adam.
Wow. Nicola, thank you. Andrew, thank you for the introduction. And Michael, thank you for everything. My name's Adam Powell. And this morning, good morning, everyone. This presentation is going to be about sealing solutions within Kaplan turbines using Chesterton's engineered polymer solutions. So just a little bit of a background. Chesterton was founded. Chesterton is an old, mature company, founded in 1884. Here in the United States, just in the Boston area. Chesterton Sealing Solutions, we're going to talk about Chesterton Sealing Solutions for the hydropower industry. Kaplan turbine runner blade seals. The checklist or the thoughts and considerations you need to take for runner blade trunnion sealing, and then we're going to open up for discussions and questions. A little bit about me. My name's Adam Powell. I've been with Chesterton for coming up for 24 years now. Originally from the United Kingdom, I did one of the old-fashioned apprenticeships with the UK Navy. Came to Chesterton, focusing. In Chesterton, we work on many different industrial applications, so we have experience in all sorts of industries. But my passion has been in marine and in hydropower. So just a little bit about Chesterton. Chesterton was founded in 1884 on the Boston waterfront. It's still located in Massachusetts. We're just a little bit north of Boston now. Our manufacturing and our corporate headquarters are in Boston or in Massachusetts. But we are a global company. We have worldwide distribution and service. We have global manufacturing. We're in excess of 1,200 people. We have locations in North America, Latin America, Europe, Middle East, and obviously in the Asia Pacific region. And Chesterton is built up in multiple business units. So we have mechanical seals, packing, industrial lubricants, and arc. And I know last year Michael gave a presentation on mechanical seals, sealing on the main shafts. This is the business group that I work in. It's Engineered Polymer Solutions. And this is what the Engineered Polymer Solutions group looks like. We have a fluid power sealing group, and that's more of the traditional, as you see, a chrome rod reciprocating, and then and holding back and sealing hydraulic fluid. And then we have a rotary component, and then we have a spring energized seal component. Our product within the EPS, the Engineered Polymer Solutions Group, we have multiple manufacturing facilities globally. So we have facilities in North America, Germany, Brazil, Chile, Mexico, Sweden, Australia, Hungary, and Italy. And that is to allow, we ship the raw materials from here to the various machining centers, and then the finished product can be machined locally, so it allows a more responsive nature to the needs that come up in the field or at the customer locations. And for sealing or key solutions for hydropower in the sealing world, we have solutions for runner blades, wicket gates, servo motors, main shaft seals. That's for the fluid sealing area of our business. And then corrosion and erosion protection in the penstocks, turbine wheels, wicket gates, and spillways. I spent some time this summer looking at some of these applications, which in older units, terrible erosion and very difficult to repair. So this is a product line that we have, but we're not going to talk about that today. And then lubricants for chain reliability. But today, with the EPS group, the Engineered Polymer Solutions team, we focus on our solutions in the hydropower industry are with runner blade seals, blade pitch, control cylinders, brake jacks, wicket gates, servo motors, and then a lot of the other sort of industrial hydraulic cylinders that you would get in any or in many industrial applications. So main gates, fish gates, spillway gates, shiplock gates, valves, you know, all those typical industrial type applications. They're all within a hydropower facility, where we particularly differentiate ourselves is with the runner blades, wicket gates, and servo motors. We as an organization have spent many, many years working within the hydro industry. We understand, or we are aware of, and we understand, and we work with many of the challenges that the industry faces. So we understand the environmental impact of an oil leakage. We understand that the equipments are older and they are subject to bearing wear. There's misalignment. There are equipment variations. Even within one power plant, there could be the same manufacturer of turbine, but there was many, many years in order to develop or to build the plant. And some of the turbines are different, even though it's the same manufacturer. And that presents itself when we're providing a sealing solution. So we look at each application, each equipment, and make sure that our solution is custom or suitable for each of the turbines within a facility. Equipment conditions vary. Installation is not always, it's always challenging, and in some cases it's very challenging. And then there's a service piece where maintenance in very short periods of time is conducted, and we can provide sealing solutions that facilitate shorter turnaround times. We're going to talk about the Kaplan turbine runner blade seals. Runner blade sealing issues, some of the things that we see, one of the main issues, obviously environmental impact. Keeping oil in the hub is critical. It used to be that as long as you had more oil in the plant that you could top up, it was okay. You wouldn't run out of oil. The hub had oil in it, you'd be fine. Nowadays, obviously, with leakage, it's critical that no oil leaves the hub. But then conversely, water going in to the hub, a very small amount of water in that lubricating oil reduces the effectiveness of the oil very, very significantly. We use this data, didn't come from us. This is sort of industry data here. 1 drop of water in a quart of oil can reduce fatigue life by almost 50%. What can cause that? Poor seal fit, poor seal design, seal materials that don't last, or the operating period that the turbine is anticipated to run between maintenance periods, corrosion, and then foaming and emulsification of the oils occurs when the moisture forms inside the hub, or when moisture gets into the hub. That reduces the lubricating characteristics of the lubricant, of the fluids, causing more wear, leading to more blade droop putting more of a challenge on the seal, resulting in subsequent leakage. So it's sort of a snowball effect. Oil leaking from the hub due to poor seal fit. This is what we do not want to see. And then the result of this is obviously oil getting out into environmental impact, pollution, downtime, and then financial penalties. this can be as a result of surface finish, seal material degradation, poor seal design. Just the basic design of the seal was never sufficient to withstand the demands of a Kaplan turbine. And this is which Chesterton comes in and will eliminate this type of leakage. We've worked over the years with many OEM hydro or Kaplan turbine designs. And in a lot of cases, we've had the benefit of receiving very comprehensive studies of blade or bushing wear or bearing support wear. When the blade droop or the trunnion wear occurs, the side loads that are occurring on the upper surface of the blade put a tremendous load on the underside of the trunnion. There's a high pressure on this upper side, a partial vacuum on the underside. So consequently, this high pressure water tends to want to push in through the trunnion. And then on the underside, that partial vacuum wants to suck the oil out of the hub. That is exaggerated as this bushing wears. As you know, in the industry, it's referred to as blade droop. Like I said, we've had the benefit of seeing many surveys and reports. And we include, if you don't know the droop or the wear in your particular turbine, we have compiled analyses over the years that we'll put in a realistic, reasonable number. And over the years, the number that we use is 1.6 millimeters of blade droop. And we found that rarely do we ever see it worse than that. So if your equipment has misalignment, which it inevitably does, our seal solution is designed to accommodate the blade droop. So you see wear here on the bushings, here on the bushings, here on the, this is transferred onto the hub. Surface finish is also critical. Depending on the location of the turbine, we see, and the nature of the water that's going through, we see different surface finishes. Some cases they're very good. Other cases there's tremendous amount of corrosion on the static surface and pitting, wear, fretting on the dynamic part of the trunnion. We understand that in many cases there's nothing that can be done in an overhaul period in many cases. So we've designed the sealing solution to address the surface finish to some extent. And like I said, we've been working with Kaplan split interlock design now for 30 years, in excess of 30 years. There are thousands of applications globally. It used to be a design that was basically a custom design for each location. It would come through engineering. We'd review all of the data. And in recent years, we as a group have been working on a suite of design software. And we've taken all of our lessons learned, compiled that into our seal design software. And now with inputs from the facility, so with the diameter of the trunnion, the diameter of the bore, the working stuffing box depth, the depth of the box minus the gland nose, we can run that through and come out with a robust standard design that incorporates all of the design features that we've developed over the past 30 years. Many of them are subtle, but each one combined or together as a group of design features, they result in a very successful sealing solution for the Kaplans. These seals are split, so it facilitates installation without removing the blade. And we replace configurations like these. There are many different, we see many different configurations of equipment. So this is a compression style seal. These are spring-loaded seals, all different types of wedge seals that are pushed down, all different types. So we'll remove these with the equipment dimensions. So the ID, the OD, the box depth. We can run a good solid replacement design that would fit into that space with minimal or no modifications. Sometimes we may make a modification to the land nose, maybe some cleaning up of the shaft or the bore if there's excessive corrosion. But that would be the replacements for these types of equipment or these types of previous sealing solutions. So this is what a Kaplan turbine runner blade trunnion split seal looks like. It is a U-cup design with an interlocking joint, and the interlocking joint comes, it's not, we don't remove any material. It's a blade cut, and when that joint comes back together, in many cases it begins to hold itself together. It begins to bond back together. It's inserted into the groove, and then when the gland nose comes down, the seal set is designed to exert an axial load, compressive load, which pushes the two seals together. So this is what the groove would look like. So the first seal goes in, and this is the oil seal. So this would be the inside of the hub. In this case, there's a spacer. We don't always use a spacer, but depending on the application, we may use a spacer. And then this seal is the exterior seal, which faces the water. So this seal's rolled, keep the oil in. This seal's rolled, keep the water out. The seal set is compressed axially, just a small amount, to ensure that the interlock joint is engaged. This is the section of a gland nose coming down and just compressing the seal set. And these sets are split, so it allows them to be opened up, wrapped around the trunnion, inserted into the groove. Then the gland nose covers are mounted, and then axial load placed on them. And that's why we need the working stuffing box depth, so that we can determine and have the appropriate seal height. This is two seals together. These ribs on the OD are used to address the corrosion of the bore. In many cases, there's pitting and corrosion, and by adding point loads, the bumps, it drives the seal into the bore and creates more of a point load and increases the sealing force on the static surface. So this is something that we look at or we use. This would be the center line here. So this is a back-to-back. This is a single back-to-back seal. It could also be two of these single U-cups just put back-to-back. This line, this single dotted line, represents the nominal equipment, the nominal trunnion, and then the dotted lines above and below represent the misalignment of the equipment as a result of blade droop. This is the point load from the bumps on the OD, creating increased sealing force on the static surface. And this represents the equipment cross section, 15 millimeters. And we have a bump on the heel providing stability, and then this additional, see this dotted line here is effectively the ghost line of the trunnion. That would be the trunnion surface. So everything past this dotted line is the interference of the seal, the sealing lip. And when that trunnion is moving, like this, the sealing lip has to follow, as the trunnion goes this way, it has to follow. But then on the opposing side, the sealing lip has to also follow, because that trunnion is moving this way and that way, and the sealing lips need to move with it. And that's why we put this wider, it's wider than the typical U-cup design, allowing the sealing lips to follow the range of motion of the trunnion through operation. And these are all the subtle features that we've learned through, I guess we've learned the hard way through many applications, many different equipment surveys. And we've compiled it now over the years. We've compiled this into one design that takes all of these small design features of a U-cup seal, but makes it very specific and unique to a Kaplan application. There's even design changes or design modifications where we compensate the diameters to ensure the joint of the seal is in compression, not only axially, but radially, so that joint doesn't tend to pull apart, it tends to push together, which is critical. These equipments, in many cases we have dimensions, but there's a variance, and there's a variance even on a single hub, and we want to make one set of seals for a hub. So we've incorporated these features to allow installation into one hub. So we have axial compression, which would be in this direction. This is the two seals back to back, the water seal and the oil seal. They're both the same design. There's no difference in the design of the seals. Just one, because of its location, it's sealing oil. The other one is sealing the water. And you'll see here the split interlock joints. There are the sealing ribs, and again, emphasis on the point ribs. Multiple sealing points on the static side. Focus load to address corroded cavity. This is a view of an installation of a split interlock. So you can see the ends of the seal come together here. The blade, this photograph was taken stood on the blade, so the blade is right out to the penstock or the turbine house wall. There's no clearance between, there is a clearance, but a very small clearance between the wall and the tip of the blade. So the seal is wrapped around the trunnion and then pushed into the box. Now, I'm not going to say this is, certainly the oil, installing the oil seal is some work. You got to compress the lips, start the seal into the opening. Once it's compressed and compressed in this direction, in this orientation, and started into the groove, then it push it down into the bottom of the box. And then the oil seal going in first, you want the lips facing the oil so that the fluid comes into the nose of the seal to energize the seal. And then on the water seal, you want the lips facing out towards the water. That one, due to the nature, it's tapered. Now when you're facing the lips out to you, it tapers in. It's an easier installation. So the oil seal is the more challenging one to install, and inevitably here, the weight of this blade is causing misalignment. So at the 12 o'clock position, you may have one cross-sectional measurement. At 3 o'clock, it'll be a different measurement. 9 o'clock and 6 o'clock, you're going to have different groove cross-sections or widths. That can be a challenge. So it generally takes a bit of work to get it in, bring the joint back together, push it to the bottom of the box, shine a light in, make sure everything's good, put the water seal in, and then when the gland segments goes on, the entire set is compressed axially, it's loaded, it's energized, and it's ready to go. The material that we're manufacturing these from is a proprietary material. It's a Chesterton polyurethane, is a thermoset material. So it's component A, component B, they come together to create the component C, the fully cured polyurethane. Its characteristics, its nature, it's very, very abrasion resistant. It has a very high elastic memory. So when the seal is compressed, it wants to go back to its original position. It's always fighting to go back to that position. And that's the initial sealing force. That's the low pressure sealing force. And as these applications are relatively low pressure, in many cases, we're relying on that elastic memory of the seal to provide sealing force in a dynamic situation where there's vibration, misalignment, sometimes poor surface finish. So that elastic memory energizes the seal, keeps it in contact with the dynamic and the static surfaces, and it's inherent in the seal material. There are many, many materials out there, rubbers, that will take a set. So they'll go in, they're easier to install, but that ease of installation is almost a reflection on how that seal its sealing ability, or its ability to provide a low pressure sealing force, because in these applications, unlike a hydraulic cylinder running at several hundred bar, these seals don't really benefit from higher working pressures. There is fluid pressure, and the water pressure is relatively high, but it's not in the hundreds of bar range. We're looking for the seal to energize itself, and then the fluid gives it that little extra boost to keep it in contact. So the material that we're using here is proven material, very robust, stable in water, high abrasion resistance, high elastic memory. This is a view of the joint coming together, and actually you can see in this view what I talked about with we really don't want the seal to be in tension at the joint. We don't want the joint to be pulling this way. If anything, we want the joint to be pushing itself together this way, and then we'll load it axially. So this is the end load that we generate. And then you'll see here, these were done these are in Quebec, northern Quebec. And this is a very fine line where the joint exists. And we often recommend marking the trunnion on the exterior where the joint is located, because after a period of time with a little bit of marine growth or some sediment, it's difficult to find that joint. So mark on the outside where the joint is, because when you come to remove them, it's helpful if you start with this piece first. You tug that out with a packing puller or something, and you pull it out, and then you can work your way around the trunnion. Prior to assembly, this is what it looks like. During assembly, it's sort of locked together. And then after assembly, you can just see this very faint line. And these surfaces, very often, when they come together and they sit there for a while, they almost need, like the ring blocks, the slip gauges, and you ring them together. That's what this is a little bit like. Those are very clean surfaces. They're not necessarily smooth, but they're mating surfaces. And when they come back together, they almost ring together. And after a period of time, you have to sort of break that joint, even though the joint was never glued or there's no adhesive there. We don't want any adhesives there. We want this to be clean. If anything, if there was a temptation to add something, you think, well, let me add something to that joint, some RTV or something, it'll help. Well, it won't. It will prevent the surfaces coming back together. If anything, you want to clean that joint, wipe it really clean, remove any greases or oils, and that will allow it to really come together, really lock in tight. The parent surfaces will come back together and begin that, I guess it's a molecular bonding, because the materials have become so close together again. So that's the interlock joint, and this is a key piece to allowing that split seal so that we can install the U-cup. So here again, that view of the seal going in. There's the interlock. Oh, and this, high abrasion resistance, elastic memory, hydrolytic stability. Now, this is a key piece. We do a tremendous amount of work for the US Navy. And one of their challenges that they faced was, by the time they make an order and they receive the order and they put it into their store system and they distribute globally with product, the shelf life was an issue, certainly for a lot of the rubber components, the soft components. It would take them more than 3 years to get product out and into the stores facility. And at that point, the shelf life was close to being expired, so they're having to replace it before they even used it. The urethane has a 25-year shelf life, no aging, no material degradation. And even this 25 years is a little bit questionable, because we need to put a number on it. I have honestly seen seal sets come back after 20 plus years of operation, and they look as good as the day they left our facility. They're obviously in a good application, but the elastic memory is still good. The surface finish it's still a good seal. So in a turbine where you're looking to get upwards of 10 years between maintenance, 7, 8, 9 years between maintenance periods, having this shelf life and then being able to store a seal at a facility without the concern of keeping an eye on lot date codes. It's very powerful. So we can have 25 years, no aging, no material degradation, very high tensile strength. You can stretch this, not that this really will be in a tensile loading environment, but it's got a high tensile strength, and it's self-lubricated, so it has very low coefficient of friction, much lower than rubbers and other compounds. Best seal for the job. So we use this chart to try and illustrate the nature of seals. So as we come to the right of the chart, you're looking at compressive style seal. So an O-ring is a compressive style of seal, and as you go to the left, you have a pure lip seal. And then somewhere in the middle, you've got a combination of the benefits. So the friction, lower friction, higher friction, lower breakaway force, higher breakaway force. So we want, with the reason we're selecting U-cups in this sort of range is that we want a seal that can tolerate equipment movement, misalignment. So on the cross section, it varies. We want to have a low wear rate, a vibration. Pure compression seals, they provide a very, very high sealing force. But in order to install that seal, you can only provide a certain amount of compressive load, otherwise a certain amount of compressive interference. If you provide too much in a compressive, you won't be able to install it. So consequently, the ability for that seal to respond to dynamic motion is reduced, because let's just say you put in 0.5 millimeter of interference. It means the equipment must move less than 0.5 millimeter. If it moves more than 0.5 millimeter, you've lost contact and consequently a leak path. U-cup designs have flared lips. Now, to bring those lips in requires a lot less force. They're installed into the equipment. The base of the seal provides that spring load or the elastic memory. Now, the lips, when they're inside the equipment, if the equipment moves, they can vary. They'll go back to where they were or anywhere in between. And they're very dynamic and responsive to equipment movement. So that's what we're looking for. We want something to respond to shock loads, to vibration, to tremors, to shuddering of the blade, to any wear in the trunnion. And that's why we look at seals at this end of the spectrum, tending away from compressive seals. The older style, there used to be many cases where it would be stack sets installed, V-ring stack sets. And V-ring stack sets work as a progressive seal. So the first sealing lip allows a little fluid by. The second sealing lip begins to stop the fluid. Third, fourth, fifth, sixth. By the time you get to the seventh sealing ring, the fluid is stopped and prevented from leaking, so we're okay. But on each of those seal rings is a very small amount of interference. So it can't accommodate misalignment. It can't accommodate the vibration as well. And they end up becoming like a plug fit. So they clamp down really tight and over time require adjustment and further axial load. And at a certain point, you can't load them anymore and they have to be exchanged. We did some testing to compare a compressive seal against a U-cup style seal. And we were looking particularly at breakaway forces. So we mounted a seal inside this holder and we supplied a load and we measured the resistive load for breakaway and then dynamic motion. Results were interesting, and I'll show you. And then we repeated this for a seal that maybe had been stationary for a period of time, stationary for, say, the plant was in a period of non-operation, and the blades hadn't been indexed for 6 months or 3 months. Are the breakaway forces different after a stationary period of time, excessive time, long period of time? Or is time not a component of the breakaway force? This was the fixture. Now this is the load extension curve we had for a typical O-ring. So the load was just being applied, no movement, load increasing, and we begin to get movement. And then as we got into the dynamic range, the load stayed fairly similar to the breakaway load. So this is the breakaway point. And then this was constant motion. And then this is a U-cup seal. So loading up, the breakaway point. After breakaway, the constant motion, the loading is significantly lower. Now in a turbine, I get it. There's a tremendous amount of force. We're trying to change a turbine, a pitch of a blade underneath a huge water force, a huge hydrodynamic load. So there's enough power there to move the blade. And there's enough power there to overcome the resistance of a seal. But when you think about the interface between the seal and the dynamic surface, these forces are going through that dynamic, they're going through that interface. So at the point where the contact point is, this is the force that's being created at the lip. And this is the force that's being created with the O-ring. So we're here, sorry, this is in imperial units, but 65 pounds force. And with the blade seal, it's 14 pounds force. So that loading that's occurring on the lip is significantly less. And then in the dynamic range, it's lower again, whereas with the O-ring, it remained fairly high, up in the 50s. So what that demonstrates or shows is that the breakaway force is less. Consequently, the sealing lip is being exposed or exerted to lower forces. So that material in the sealing lip is under less force, less wear on the equipment, less wear of the seal, longer life, and in the dynamic range, even lower again. So you're really in a situation where you've got this seal that's putting less load on itself, providing adequate sealing, have a wide range of dynamic capability with a relatively low load through its operating life, giving you or resulting in a longer operating life. So these are all pieces that we have explored over the years and fed back into the designs. This is a little bit of a data sheet. It is the data sheet on AWC 800 polyurethane, all done with standardized testing and the resulting data. I mean, essentially, it's a high elastic memory, hydrolytically stable, and very abrasive. So when we're looking at designing a solution for a Kaplan turbine, we appreciate, and in reality is sometimes, in many cases, there's nothing we can do to modify, change the turbine. But if we understand the condition, the size, any history, then we can develop a sealing solution that's specific to application. So exact turbine and blade measurements, no technical specification or international standards for designing runner blades. Even within the same manufacturer, there are different sealing solutions. There's different geometry. Over the years, there's been developments and changes, and we've seen that even within the same powerhouse. Turbine 1 will have a slightly different configuration than turbine number 6 or 7. So requires some retrofitting of seal solutions. Checking seal cavity cross-section values around the blade trunnion. Because of blade droop, the seal cross-section will vary 12 o'clock, 6 o'clock, 3 o'clock, 9 o'clock. If you average them out, you will actually come back with the nominal equipment cross-section. We will design a seal to fit that nominal cross-section and incorporate in all of the designs a 1.6 millimeter blade droop. And if you were to tell us, and I don't think we've done one that's greater than 1.6. We may have done, and if you were to tell us that a particular application was greater than that, then that would become special design, custom design. So we say here the recommended number of measuring locations on these larger, although these today, these aren't actually that large. We see much larger than this. But right across the range, measure the cross-section, measure the diameters, and then we can develop a solution. And this is what we mean by going around. So 12 o'clock, 6 o'clock, what are you getting for cross-sections? And this is an actual report from a customer. And this is ideal world that we would have these dimensions. In many cases, they're not available. So we can work with whatever's available. The more information we have, the more custom we can develop the solution. Get the turbine blade measurements, the cross section, check and resolve equipment condition. So if there's a lot of pitting or corrosion, if it can be cleaned, that helps. If it can't, report to us what the condition is, and we can modify accordingly. So the scratches and scores, wear of the trunnion from previous sealing solutions, abrasion in some plants where the river water is so full of sediment that becomes like a grinding paste. That creates some issues. Corrosion, pitting from by the water. So I said that we have manufacturing facilities globally. All of those facilities will be using AWC 800, the polyurethane. The designs now used to all be done in Groveland. So we would get the data and we would run it through our system, and we would come up with a Kaplan seal design. We've now put that into, it actually will be in the controller of the CNC, and that will allow for standardized split interlock Kaplan sealing solutions to be manufactured anywhere that we have a Chesterton facility. And if it was manufactured in Latin America, North America, Australia, the design parameters will all be the same. So that's a nice feature and function that allows repeatability, constant design. And then when we have a seal, if we were to have an upgrade or a design revision, we can incorporate that into the software. So in Custom Seal Australia, we have the polymer seals, sealing kits, cylinder seal kits, hydraulic seals, rotary seals, and the spring energized seals. So it's a full capability in Chesterton Custom Seal, which would be your quote unquote local provider. And that brings us to the end of the presentation. And this, if you were to, I'll leave this up. If you were to scan on this QR code, it takes you to a white paper that was presented on the Kaplan turbine sealing solutions from Chesterton. And that was presented in Europe.
Thank you, Adam. That's fantastic. Yeah, that QR code will allow you to download that white paper. So you should be able to reference that for future. And so, yeah, at this point in time, again, thank you, Adam. That's fantastic information and some great learnings from our past experiences around the world. Open the floor, I guess. You have a question section or a little question box if anyone has any questions, or I'm not sure, Nicola, if we want to open up microphones or how it's going to work, but let's see how we go. Questions come in. Can you offer the segmented seals oversized on the ID so the customer can machine to suit wear of the shaft sleeve?
No. The nature of the machining process is such that we take a billet and we machine the IDs and the ODs, and because of this material is, when you take a machinist that's machining metal for years and they come to machine polymer, it drives them a little bit crazy for a while, because as the tool comes in, because of the elastic memory of the material moves away from the tool. So you rough the material up. So what has to happen is you have to come in and take a committed cut. So you come in, take this, and it's a heavy cut. So once that seal is finished, if you were to mount it up again and try and take, say, 1 millimeter off, all that happens is the urethane moves away from the tool. And when the tool goes past, it moves back again. And it just roughs the surface up. So this is where we partner with, we have the benefit of a broad sales group, field service people. They can work to get the equipment dimensions, and then we'll machine it to that size. And it doesn't matter what the size is within the range. So if you already machined the diameter down, we'll make it to fit that diameter, even if it's a quote unquote odd diameter, non-nominal dimension. It doesn't matter. Somewhere in between metric and inch, an odd metric size, you clean it up enough to improve the surface finish, we'll make the seal to fit. But unfortunately, we can't make a semi-finished product, supply it to allow it to be finished on site.
And this is why, as you said, we work with our local sales team and engineering team, and in New Zealand's case, it's CGI, and Craig and Graham and Alistair are there to assist in those sort of measurements and ensure that we have the right dimensions. So
and ask, you know, we talk about, do we have all the dimensions? We look at the dimensions before we work together as a team prior to creating any design.
So another question's come in, are you able to offer fast turnaround on the case that during an outage, the shaft measurements can be provided to you and a quick supply offered?
We are so much faster today than I guess it's never fast enough. We are so much faster today than we were when I started with the company. When I started with the company, we were making this type of seal, and it was a molded seal. So we would get the information from the facility. We'd have to make a mold, and then to process that mold, making the mold took weeks. It was made out of aluminium. It had to be designed first, and it had to be plate, had to be purchased, and the mold was cut. So it was months to get a seal solution. Now we pour billets with the urethane. The billets are fully cured, so that's a very stable material. We enter the data into the machine code, run the design, and we can machine it. So we are significantly faster. And I would say, yes, we can respond to situations where you pull that hub apart, you look and go, oh dear, this is a different dimension than we thought. Or the corrosion or the pitting was so bad, we have to machine it, and now we need a different size. Yeah, we can respond to it. And significantly, I would have said 10 years ago, it was weeks, maybe even months. Weeks, certainly weeks. Now we can respond really as quickly as we can move logistics.
Yeah, it's more like days these days.
Yeah, it's days now, and most of that is the logistical piece of people moving and coming in, and
measurements and stuff. Exactly.
Yeah.
Does Chesterton have examples of seals for other locations around the machine? If I contact you directly, I'm thinking of a Francine runner.
On a Francis turbine?
I guess so, yeah. It's from Emma. We might need to get some more information about this one.
What on the wicket gates for a Francis turbine?
Yeah, she says a runner base ring sealing arrangement. So we might ask Emma to send us some information.
Yeah, we've certainly. So with Kaplan turbines and with Francis turbines, they both utilize wicket gates to control that flow onto the turbine. And we do upper and lower seals on the wicket gates. The servo motors that control the wicket gates. In Peltons, we do the nozzle, the cylinders that control the nozzle. So yeah, we've done many applications within hydro, and we'd be happy. Personally, I love talking about, listening to and talking about hydro applications. So yeah, we can, and we'll be very candid if it's something that's not in our expertise. We'll tell you.
So if you could switch to the next slide, because that's where
our
contact details are, then Emma can send us an email And either George, Michael, or Andrew, it's no issue, and we'll cover back to you. Another question, Adam, does Chesterton offer a water filtration system for shafts sealing water for high sediment systems when a multiple seal arrangement is used?
Oh, it's not as big an issue with the EPS, the Engineered Polymer Solutions seals. Because of that lip load and the contact, and we remain in contact, the sediment tends not to get under the lip. We actually see a very discrete line where the sediment ends, and it's at the contact point of the seal. But with the mechanical seals, they do require or benefit from a flush control mechanism. And I remember one particular application up in the Yukon, I think, and the river looked like it would look like chocolate flowing down. I mean, it was so much sediment, and I know there was a fairly comprehensive flush system to protect the faces on the main shaft seals.
Yeah, so that's true, and I guess it is an application by application specific answer. So depending on what sort of sediment you have, etc., sometimes mechanical seal faces can cope with those on the main shaft sealing.
I always like to say that in any application, hydro, in any industrial application, we have the technical information, so the temperature, pressure, the speed, the surface finish, and all of that stuff. Then we have the story, what's going on, what's unique. And every plant, we want to know what is unique, what's happening with this application. And then there's the backstory. What have you tried? What's not worked? What's the goal? What are we trying to get? Are we trying to improve life from 1 week to 2 weeks? Or are we trying to improve life from 1 week to 5 years? Knowing the goal and the story and the application details gives us that broad picture, because we want to take all of that into consideration when we make a recommendation for a solution. It's not just about the temperature, pressure, speed. So yes, we have excessive in the springtime. There's excessive sediment in the fluid flow, and we've noticed over the years that this leads to significant abrasion. What can we do? And we'll be happy to look at that.
Yeah. Absolutely right. Correct. Another question is, do Chesterton offer water lubricated bearing and seal systems for vertical machines?
These, I know what you mean. These are the polymer bushings. We don't.
Line shaft, yeah. Line shaft.
Yeah, we don't.
How do you compare Chesterton's products with other suppliers in a negative pressure situation due to cavitation, etc.?
The distinct feature about the lip load, so that elastic memory of the seal is where we differentiate that, and the ability of it to flex and move with the equipment. So when you get the negative, so even on the upper surface of the blade, there's a high positive pressure, and on the underside, it's causing this is what causes the rotational, the differential loading. There's a negative pressure trying to suck the oil out, and it's the elastic memory of the material, its cross-sectional fit into the equipment that differentiates from other seals. Many other seals will go in, or seal materials will go in, and they provide some sealing force, but the goal is to maintain that sealing force over the operating life. And as we all know, rubbers and other compounds take a set after a period of time. Once that set has occurred, you've lost a lot of that sealing force, and if the equipment moves or there's negative pressures, it pulls the lip down, and now you have a leak path. So it goes back to it really goes back to the inherent nature of the material.
I was about to say that it was a combination of material and the profile that helps in that application.
Yeah.
Okay, that's good. There is Yeah, there seems to cover all the questions as such. There's a statement that's from one of the people that we know very well that talks about the opportunity that Chesterton Custom Seal can supply really any type of sealing, whether it's from the main inlet valve to the draft tubes, etc., everything in between, and as long as it's round, we will find a solution for it. So, good comment. Thank you, David. So anyway, that looks like the end of the questions at this point. Thanks to you, Adam.
You're welcome.
Andrew, all good?
Yeah, thanks for that, guys. I really appreciate you taking the time, obviously, yeah, really appreciate that. So yeah, thanks to everyone that's come online. Just like to remind everybody that obviously we've had a request for submissions for our conference that's going to be in Hamilton next year. I'm sure a number of you have had emails about that. So April of next year, obviously with a couple of day conference, you know, culminating in dinner at Hobbiton. So if that doesn't appeal to anybody to come to a conference, I don't know what will. Beers at the Green Dragon Inn, you know, so be there or be square. So yeah, look, get those submissions together. Obviously, we're looking for things for the end of September, so we can tidy up the program for that. So, but yeah, we would probably do another one or two of these towards the end of the year. We've got yeah, and I look forward to seeing you all there. And yeah, thanks again, and hope you have a good rest of the day. And a special thank you, Adam, Michael, you know, for coming along to do this, and yeah, and sharing your experience.
My pleasure. Thanks for inviting us, and anyone on the call, if you have questions, you have anything you want to, we're happy to talk about it. We're happy to look at applications.
Yep, just send us an email. There's 3 options there on the screen, so take your pick. Absolutely happy to help. And as I said, we do have local representation in New Zealand, so we can certainly point you in the right direction.
Okay, thanks everybody.
All right, have a nice day, everyone.
Thank
Okay,
you.
bye.
Bye.